All right. So that's the first suggested problem. So this 36 from your book, determine the currents I1, I2, and I3. Okay, I1, I2, and I3. In figure 53, assume the internal resistance of each battery is R is equal to 1 ohm. Okay, the batteries seem to have internal resistance, 1 ohm each. And B, what is the terminal voltage of the 6-volt battery? There we have two batteries. One is 6 volt, the other is 12 volts. And we want to find the terminal voltage of the 6-volt battery. And there are like resistances here. Okay, so obviously we will use Kirchhoff laws. There's no other way I can solve this problem. So let's just start with the first one. Okay, the loop rule. Okay, maybe I can start with junction rule. So here that I need to find a junction, let me find this one. And here I2 is going away from the junction, I1 is coming into junction, and I2 is going away from the junction. That means I1 is equal to I2 plus I3. I1 is equal to I2 plus I3. Okay. Okay. The second one is loop rule. Let's form some loops. So maybe I can start with this part, something like that. Let this be my loop. And if I do the red loop, let's call this red loop gives, okay, where should I start from? So the current is going this way. Okay, the current is going this way. So I can calculate all the resistances and multiply it with I1. And since the loop and the current are in the same direction, I'll get a minus sign. So this one is 12 plus 22 plus 1. 12 plus 22 is equal to 35. This is going to be minus 35 times I1. And I have the battery here. I'm going from smaller to larger, so this is going to be plus. This is plus 12. And now I finish this upper branch from here to here. I need to add this part. Let me, okay, this is also current and loop in the same direction, so it is going to be minus, the resistance is 12, right? 11 plus 1, 12 times I2, and the battery is going from small to large, so large minus small is positive, so it's going to be 12 volts. Okay, now I'm back to where I started, so this is a complete loop, so loop rule says this should be 0. Okay, let's form another loop. For example, I can form an orange loop. Let's call this way. And let this loop be also counterclockwise, which doesn't matter, but let's just choose. So I don't know, is this orange? Orange loop. So this should be, okay, here my current and the loop are in the opposite direction. So, and the total resistance is 11 plus 1, 12. This is going to be plus 12 I2. So this is plus 12 I2. And battery is going from large to small. So small minus large is a minus. So it is going to be minus 12. So now I'm here. The current and the loop are in the same direction. So this is going to be 15 plus 18 plus 1. What is it? 15 plus 18 plus 1. This is 34. And since I'm in the same direction, this is going to be minus 34 times I3, and the battery is from small to large. Large minus small is a positive, so this is going to be plus 6. So now I'm back to where I started. So the loop rule says this should be equal to 0. So again, this is like an exercise for you. You can form another loop like this loop, and check that this condition doesn't give anything extra. Check what you get from this loop. Check, okay? Now let's look at the equations and see what I can do. So my unknowns are I1, I2, and I3, 3 unknowns, and I have 1, 2, and 3 equations. So I'm in good shape. So I can solve 3 unknowns with 3 equations. So I look at the first equation, it is in terms of I1 and I2. And I look at the second equation, it's in terms of I2 and I3. So both equations have I2. So I can write I1 in terms of I2, I3 in terms of I2, plug everything in here and solve in terms of I2, and then I'm done. Okay? So I1 from the first equation is going to be equal to 24 divided by 35 minus 12 over 35 I2. Okay. And now the I3 from the second equation, or like third equation, I3 is equal to 13 divided by what? 13 divided by 34. That's helpful. Okay. And then this is, okay, good. Thank you. Good job. Okay, this is 12. Yes, exactly. So this is 12 divided by 34 times I2 and minus 6 divided by 34. Okay. Now I use these equations with this one. So I1 is, okay, let's copy, not write over and over again. I copy this one, copy, paste. This is I1, and this should be equal to I2 plus I3, and I3, let's copy I3 from here. Copy, paste, something like that. So now collect all the I2s on one side. I2, I have 1 plus 12 over 34 plus 12 over 35. This should be equal to 24 over 35 plus 6 over 34. Some funny numbers, but hopefully we got them right. Okay, let me pull this guy to here and calculate. 0.508. Okay, I2 is equal to 0.508 ampere. Now I1 is equal to, from here, what? 0. Almost the same, 511 ampere. So that means the other one is almost 0, right? So this is I3 is equal to 2I, okay, it's almost like 3 milliampere. Good, so this whole calculation was for A. And B, what is the terminal voltage of 6-volt battery? A is equal to, okay, I'll just do it because you know what it is. 6-volt battery has I3 times 1 ohm. So this is going to be equal to 6, okay, 6 minus Okay, minus this number, minus 6, 5.99. This is 5.99 volts. Okay. In the orange loop coefficient of I2. So I2 is this way, right? So the loop is going in the opposite way of the current we choose. And the total resistance is like this internal resistance 1 ohm plus 11, 12, and 12 times I2, and it is positive because we are in the opposite direction. Is that clear? So the rule is if you are going in the same direction with the current, the resistance like delta V is minus. If you are in the opposite, the potential drop is positive. And that makes sense, right? So here, if you think about that, going from here to here, like there's obviously a current along this direction. That means the potential here is bigger than potential here. Then when you traverse in the opposite direction in your loop, delta V is what? Final minus initial. So this whole thing should be positive because you are going from a low potential to high potential. Next question. This is 49. Consider the circuit shown in figure where all resistors have the same resistance R. At T is equal to 0 with the capacitor C uncharged, the switch is closed. At T is equal to 0, the three currents can be determined by analyzing a simpler but equivalent circuit. Identify this simpler circuit and use it to find the values I1, I2, and I3 at T is equal to 0. At B, at T is equal to infinity, the currents can be determined by analyzing a simpler equivalent circuit. Identify the simpler circuit and implement and finding the values of I1, I2, and I3 at T is equal to infinity. And C at T is equal to infinity, what is the potential difference across the capacitor? So let's start with A. Simpler the current to find the three currents. It's simpler but equivalent, right? At T is equal to 0 with capacitor uncharged, switch is closed. At T is equal to 0, the three currents can be determined by analyzing a simpler but equivalent circuit. So what is the simpler circuit at T is equal to 0? Maybe I can copy this circuit. Let's simplify this circuit. What is it? So simplifying a circuit means removing some stuff. What can I remove from here? And T is equal to 0. When you first close the switch, the capacitor is uncharged. And this capacitor will start accepting charge as if this whole thing is connected without a resistance, right? It's almost as if this is like a single wire. So this rest of the circuit will not know if there is a capacitor here. So the simpler circuit is you just close this guy, and this is like a wire without resistance. Okay? And if this is the case, this is basically like simple R, these two guys are parallel. This guy's series, so this is going to be, okay. REQ is simple, right? R plus, what is it? 2R, is it 2R? These two guys are 1 over R plus 1 over R to the minus 1. And this one is going to be equal to, okay, this is 2 over R plus R over 2. This is going to be 3R over 2. And in this case, I1 is equal to E divided by resistance 3R over 2, which is equal to 2 times E divided by 3R. And I2 and I3 are 2 are equal, and they should be half of this current. So it's going to be E over 3R. So this was for t is equal to 0. And B, let's look at B. At t is equal to infinity, currents can be determined by analyzing a simpler equivalent circuit. Let's go with B. And let's just copy the same circuit. So now I said simplifying circuit means kind of eliminating things. What should I eliminate at t is equal to infinity? So this is again, I remind you, t is equal to infinity. At t is equal to infinity, the capacitor is completely charged. So it cannot accept any more charges. So this whole branch of circuit will be almost as if it's like an open switch. Or you can just think of this whole thing does not exist. Like remove from your circuit. And then the simpler circuit is this part. And in this case, okay, I think we know how to find it. So I1 is equal to I2 is equal to, in this case, E over R. R is 2R here. And I3 is going to be equal to 0. Okay. So, and finally C, at t is equal to infinity, what's the potential difference across the capacitor? The potential difference across the capacitor at t is equal to infinity is exactly the same as the potential difference across this guy. And for this, we can calculate that. So V is equal to, for that guy, it's going to be current times resistance, but current we just found, okay, it is like I2 times resistance. It's going to be E over 2R times R. It's going to be E over 2. So in the part B, I'm saying that if you wait infinitely long, the capacitor will take as much charge as it can ever take. And basically you just fill the bucket completely. And once it's filled, it cannot take anything else. If it cannot take anything else, if the capacitor is full, that means nothing can come from here, or nothing can go from here. So this whole thing is almost like an open switch, exactly like you said. And if it's like an open switch, I can forget about this branch, just forget about this, and solve my problem for this part. And in the last part, it's asking what is the potential difference. I mean, this capacitor is connected to this resistor in parallel. So if I find the potential difference across this resistor, I find the potential difference across the capacitor. And of course, here I have to be careful. There is no potential on this resistor because there is no current. All the potential difference here is coming from the capacitor, which is like the charge accumulated on the capacitor. Good. So for the circuit shown in figure, show that the decrease in energy stored in the capacitor from t is equal to 0 until one time constant has elapsed equals the energy dissipated as heat in the resistor. So the amount of charge, the amount of energy left from C should be equal to amount of energy dissipated from the resistor. That's what we need to show, right? So does anybody remember the energy in the capacitor? So if you forget, it's actually very simple, right? So we say energy is equal to some little charge times potential difference, and C is equal to Q over V. So I can put this like dQ, okay, let's put this bigger Q, dQ V is equal to Q over C. If I integrate, okay, this is little u. If I integrate both sides, u should be equal to 1/2 Q squared over C. And if I use different relations, this should be equal to, okay, Q over C is equal to V. It's 1/2 QV. And this is equal to, I can put like Q squared over C squared times C. Q over C is equal to 1/2 C V squared, whichever you like, right? For that, I'm going to use this one. This is equal to 1/2 Q squared over C. And I know the capacitor has something like this. We just found Q as a function of T is equal to some Q0 e to the minus T over RC. And then the one-time constant passed, Q will be equal to Q0 times e to the minus 1. So let's find U. Delta U is equal to, okay, this is capacitor, U2 minus U1. That's how much energy changed. So this is 1/2 Q0 squared e to the minus 2. So square root of e to the minus 1 is e to the minus 2 divided by C, 1/2 Q squared C, minus initial, this is 1/2 Q0 squared over C. So the difference is what? 1/2 Q0 squared over C, 1 over E squared minus 1, which is like a smaller than 0, right? Negative. It is decreasing, like decreasing. So how about the resistor? How do I calculate the energy dissipated in a resistor? Or maybe I can ask you, what is the power of a resistor, P? Does anybody remember? Or I squared times R, right? Good, yes. Power is I squared over R, and I know this is equal to du dt. Then delta U is equal to integral I square R dt, and t from 0 to 1 times constant, which is RC. And I obtained from current. I is equal to minus dq dt, which should be equal to q0 over RC e to the minus t over RC. Then this guy is equal to 0 to RC, q0 squared R squared C squared e to the minus 2t over RC times R times dt. So let's cancel with this one. And I can take this integral. This is q0 squared over R C squared e to the minus 2t over RC divided by minus 2 over RC, and the limits from 0 to RC. And let's cancel a little bit more. This R and this R, this C and this C. And this should be equal to Q0 squared divided by C. And there's like 1/2 here. I'll take it out. So this is 2. And if I put RC is equal to minus e to the, okay, e to the minus 2 times t is equal to RC divided by RC is equal to e to the minus 2 minus minus plus e to the 0 is 1. Okay, good. And you can see, okay, this is the resistor. So what we find is delta U capacitor plus delta U resistor is equal to 0 as it should be. Okay, so as it should be. Okay, last question. This is 71. A Wheatstone bridge is a type of bridge circuit used to make measurements of resistance. The unknown resistance to be measured at Rx is placed in the circuit with accurately known resistances R1, R2, and R3. One of these, R3, is a variable resistor which is adjusted so that when the switch is closed momentarily, the ammeter A here shows zero current flow. A, determine Rx in terms of R1, R2, and R3, and B, if a Wheatstone bridge is balanced, it means there's no current here, and R1 is equal to R2 is equal to R3 is equal to this. What is the value of unknown resistance? What should we use? Potential difference. So yes, I ask you, if there is no current between B and D, so between current B and D, there's no potential difference. What does that mean? There's no potential difference from B to D, or okay, if there's no current from B to D, what does that mean for the potential difference? What should the potential difference be between B and D so that there's no current here? Exactly, right? They have to have the same potential, so there's no current. Thank you. Can I use Kirchhoff law? Kirchhoff's laws. Maybe I can tell you this. I want to form two loops. I mean, there might be different ways to solve this problem. So I will form a loop like this, blue loop, and I will form a loop like this. Red loop and blue loop. So let me just write the Kirchhoff laws and look at that if that's helpful. So red loop is what? So the current and the loop are in the same direction. So this is minus. So this is minus I3 times R. And from here to here, there's no potential drop. So I have nothing. And from here to here, I'm against the current. So it is going to be plus. This should be equal to plus I1 times R1 and is equal to 0. So the blue loop starts from here. The current and Rx are in the same direction, and obviously this current should continue. There is nowhere else to go. So it's going to be I3 times Rx, but the current and the loop are in the same direction, so this is minus. And in the other one, I'm like against the loop, so it's going to be plus I1 times R2 is equal to 0. So from the first one, I get I1 R1 is equal to I3R, or I1 over I3 is equal to R over R1. From the second one, I1 R2 is equal to I3 Rx, then I1 over I3 is equal to Rx over R2, but these ratios are the same. This means R over R1 should be equal to Rx over R2. Then Rx is equal to R times R2. Okay, I forgot one of the R. So this one is 3, right? This is 3. So this one is 3. This one is 3. This one is 3. So Rx is equal to R2, R3. Let's write them. R2, R3 divided by R1. So basically, product of R2 and R3 should be equal to product of Rx and R1. Okay, that's the Wheatstone rule, or that's the condition for balanced Wheatstone bridge. So this one was A. For B is just numbers. So Rx is equal to R2 is 972, R3 is 78.6, and R1, so this is 2, 3, and R1 is 630. And if you do this, I found 121.3 ohm. Yes, thank you. I got the same thing. And that's it. You're done. I think, do I have anything? No, that's it.